Hello, my name is Kayvon Haravi, and I will be presenting the paper DEMA, Enhancing Causal Analysis Through Data Enrichment and Discovery in Data Lakes. This work is authored by myself, Kayvon Haravi, Sathvik Durasala, and Babak Salimi, and we are all from UC San Diego. First off, we want to give a quick little background on causal inference and causal analysis. And we'll start off with the very common or famous statistic adage, correlation does not imply causation. And we may have the pseudo data from New York that says low ice cream sales result in more car crashes. And maybe this will result in the state of New York to say, well, let's go and get rid of, or let's go ahead and put more ice cream trucks on the streets, and that should get rid of all car crashes. So win-win for everybody. But obviously, common sense should prevail, and we should probably not do that. And we have some sort of underlying confounding association, such as weather. And an explanation of this is that weather can be impacting our ice cream trucks or ice cream sales, where on rainier days, it turns out that we have less ice cream trucks on the streets, so low ice cream sales. And rainier days, we have more taxi collisions. So that could be a common sense finding that we have. But we need to find this out without using our common sense. And so what we use is double machine learning. And we use double machine learning to control for this weather covariate and to find the true causal relationship between the ice cream trucks or ice cream sales and car crashes. And a little quick explanation of double machine learning. This is a methodology that integrates both propensity scores, which estimates the likelihood of receiving treatment given certain covariates, and prognostic scores, which predict the outcomes without the treatment. By combining these two approaches, double ML will ensure robust causal effect estimation, and it is very good in the area of high covariates, and the reason why we are using it. And one of the reasons why we are using this with data lakes is data lakes are instrumental in modern applications. They allow for large storage of data in which we can apply analytic techniques, as shown in this graph, with streaming analytics, business intelligence, data science, and machine learning. Our goal is to query this large data lake, such as a New York City data lake, and find relevant tables for the purpose of causal analysis. And talking about our paper and our pipeline, we have the acronym of DEMA spelled out with Data Enrichment and Merging for Causal Analysis Pipeline. Here, we will go ahead and throughout this presentation explain these steps, but this is just a picture of our pipeline. We start with our base table, the data lake, do data discovery, and then we have our steps to find out the impacts and join viability and integration and aggregation. And we will output a data set report and a curated data set that is the most comprehensive that we can come up with. So first, starting off, we have our user query as shown by that last pipeline, where a user might have a data set of New York City taxi collisions, and they ask, what is causing taxi collisions in New York City? And what we will go ahead and do is this user might ask, what other tables can I access from this data lake? So we will go ahead and search through this New York City data lake, and with using our search key of crash date, we will go through relevant tables that are all inside this New York City data lake, whether that be weather, projects, constructions, and many more. We will get a returned ranking score of these candidate tables. This ranking score has no indication of importance, but can just tell us which ones has the most overlap to least overlap, as this can just be helpful, but is no implication of importance or causal impacts. Then our next step is to do joint viability assessment. And this joint viability assessment is to ensure that when we do joins with these multiple tables, that we don't have empty and sparse tables, as this is a very common thing to have with joining this many tables from a data lake. And in addition, we make sure to cover other areas that we may need to check for, such as missingness of data. And I'll explain this one right here with this example, which is we have on the top left our base table that the user provided us. And then we have our candidate table that our data discovery provided us. In our top right table, we have a construction table, which has a submission date, which is we'll be using to merge with our base table. And it has borough, pole type, and equipment installed. And so what may be happening is that when we go ahead and join these two tables, we're left with tables that are, in a sense, only reflective of construction days. But we don't have that as an attribute that's actually set for us. So we can't actually control for this or account for this. So one of the ways we do this in our joint viability is that we go ahead and in this abbreviated table to go ahead and make a new attribute that just plainly binarizes if this exists in our construction table. Our base table, does it exist in this candidate table? And I will go ahead and show the results of this later, but this allows us to measure for something that we didn't have before, because as you see here with 150 and 151 collisions, we're not seeing a high variance of crashes, and maybe it might just show that all days with construction has really high accidents, but we can't really control for that because when we join them, we're not getting that. So here we're able to show and account for that. Then our next step would be data integration and aggregation. And in this step, we are just doing merging of the two tables. And if we have multiple tables or multiple tuples, then we'll do some aggregation. And in this case, we're doing a mean aggregation where on this search key that we will have air temperature and dew point precipitation. We'll go ahead and aggregate those on their median and then join that into our table. Now, we do also sensitivity analysis to ensure that in all types of aggregation methods that we do account for it. So we do sensitivity analysis. And then we do an impact assessment. And then the impact assessment, we will actually go through and iteratively, in our first step, go ahead and iteratively join our tables and apply our double ML, and then find out which is the most impactful. And so to start off with this first figure, we start off with our crash date and number of collisions, our base table. And in our base table, we have just crash date, number of collisions. We're able to featureize this with making it into year, months, days, and our number of collisions. And we use this featureized table, and then we join it with all of our candidate tables, like we were showing earlier, and then double machine learning, and we get this final report. And in this final report, we can say that turns out weather has the highest average coefficient, and just for the treatment of precipitation. So we're seeing that precipitation has the highest impact on the rest of our crashes. Then we see some other things such as wind, updates, transfers, manufacturers, where our featureized attributes actually were pretty strong, where we have months. Months is an indicator can be of crashes, updates, where the year, maybe in that certain year, we had more collisions, more rain maybe, or whatever it may be. And then we get the result of taxi collisions in New York City. So from that previous table, that was our iterative run through. And so here we're just showing the results of our recursive run through. So in a sense, we want to make sure that we get all of our most relevant tables, and we want to try and combine them together and merge so that we can have a more comprehensive data set, so that we can find out we have a more comprehensive data set, so we should get a more accurate causal effect estimation. So here we have our base table, and with our featureized base table, we find out that the year of the year that we had is the most impactful on collisions, and then the month is the most impactful on collisions. Then we go ahead and add our weather table like we were showing earlier that has precipitation and air temperature. And precipitation and air temperature is the most impactful on our outcome. So we see that this has the most output on our car crashes. And when we go ahead and apply our project status tables, then we still see our precipitation and air temperature covariates are still the most impactful. And then when we add our manufacturers table, we get precipitation and crash month becomes our most impactful. So here we're now saying that maybe our months are more indicative of our collisions. So in this final run through in our third iteration, or I guess fourth iteration in this case, we could say that we have the most comprehensive data set and then the most comprehensive results showing that precipitation is the most important in terms of our collisions. But we also could say that crash month is more important than the air temperature. So maybe, for reasons such as traffic in summer, or maybe more precipitation in certain months, whatever that reasoning may be, we would need more observational data, but this is just from our observational data. And to show this from our earlier results, from our joint viability assessment that we were talking about earlier, we actually do find some impact that we weren't able to find before. So before we were not able to find pole construction as having a good impact on our collisions in the city because we were just doing the joins and those joins having no real association between the two. And when we do pole constructions, as using that missingness example I showed earlier, we see that we get a much higher we get a much higher coefficient and a much more higher impact, saying that days where there are construction does intend to have more days of collisions with taxis. And for another scenario that we did, just to show the final results of this, we have our um, iterations here. We start with we want to find out what is a good indicator of school performance. And so we have our base table and we find out the district and your school level is the most impactful for your school performance. And then when we do these recursive joins after applying our DEMA pipeline, we get that in our PE teachers table, when we apply that, we get a ratio of teachers to students is the most impactful and our district. But then when we make our data set more comprehensive, we add math and our discipline tables, we actually tend to find out that the math level for and the amount of profanity used at the school is the highest impact for a school performance. So if you are a school, maybe these are the areas you would want to use. Uh, Make sure that you have good math skills or good math education and good disciplinary skills on profane language to ensure that you have a better school performance. And in summary, we created a novel framework that integrates relevant data from varied sources to facilitate robust causal analysis. DEMA addresses high dimensional covariates, covariate selection, missing data, and incomplete joins. We use double ML to control for these confounding factors and those high dimensional covariates. And we do this to uncover meaningful causal relationships and enhancing data accuracy to improve the reliability of machine learning models. And that is DEMA. Thank you.